is a lot more recent. This is maybe a few years ago. We have 4 different materials: hard, soft, expanding and contracting and expanding. 4 materials. We ask evolution to try to make a machine, evolve a machine that can walk out of these machines, and we get a lot of these materials, and we get much more interesting kinds of robots. And there's lots of them kind of crawling around here in simulation. Lots of interesting ideas of how evolution puts together these 4 different materials to make machines that can move. So again, you can see the evolutionary process is very similar, but the simulation allows us to do a lot more, and this is part of sort of progress. So actually, one of the biggest challenges for us is that how do we make these machines? We could make the rigid bodies robots, but we never had a material that would allow us to actually make this until recently. This is actually material we developed from a few months ago. It's electrically actuated polymer. This is accelerated about 20 times. It's slow, but you actuate it and expands and contracts, and you can build things with it. And I'm hoping we'll be able to bring these robots from simulation into reality using this kind of material. So there's an example, sort of a thread, but I want to go back to our story. What happened after we built these first robots in the lab, 2001. That was my postdoc. It was a great success. We had these robots crawling around, lots of very beautiful pictures to show to the media, and we got onto the front page of New York Times with this title of Robots Making Robots, and the story goes on to say how it's the end of the world and all kinds of things like that. So great publicity, and really that's all you need to get a faculty position. Just need good publicity, and that's what got me my faculty position at Cornell, which again on a good day looks like this. And this is actually, for some reason, a very low resolution. I don't know why the screen is taking it down, but the actual photo is beautiful and crisp, and it's a great place to be. And when I started my position there, I knew that I am not going to get tenure in a mechanical engineering department making plastic robots. There's no way. I got to make robots out of titanium. And this is what first thing we built a really, really impressive robot made of actually aluminum, but looks the same. Lots of tubes and actuators and a paintball canister in the center, valves, and this thing is really, really difficult to control. And I thought, if I can use these evolutionary algorithms to make this robot run and gallop through the fields, I'm going to get tenure. Because this is something that nobody else knew how to do, very difficult from a control theory point of view. Nobody was able to do that until recently. Nobody had any kind of galloping robots. And this robot had the power density to be able to do flips in the air, and all it needed is a good brain. So we took this robot, we put it into a big cage in the basement. This is a cage where you can see the robot there in the corner. There is also a camera at the top left. The camera is seeing the robot. And what we're doing, so this is the camera view. If it wasn't this occlusion there, you can see it. What the camera sees, and the camera sees the robot and can give feedback on how fast the robot is moving. And now, in parallel, what we did is we evolved controllers to control this robot and see how fast it moves forward. So we had a sort of a neural network that sends commands to the valves. The valves turn on and off air pressure at various places, and the hope is that some neural networks would be better than others. And if we leave this thing running for long enough, it will learn how to gallop in the fields. And so it's doing this thing here in the cage, and there's something that reels back the robot after it's gone to the other side and so on, and it's fairly automatic. And so we left this thing running for overnight, and we started getting interesting behavior. So you can see one robot. It sounds like we don't have sound. Oh, there is very weak sounds. That's the student who did this is describing it. All you need to hear is the clickety-clack of the robot, and it's kind of learning how to move on its own, so it's playing back some of what it learned. But I have to say, I saw this, and I knew that I am not going to get tenure. This is a far cry from galloping in the fields. and we're not going to take the world anytime soon with this kind of thing. There's still a long way to go. So to summarize, I already showed you two projects. The first one, I want to contrast them a little bit. So the first project we did evolution in simulation. We wrote our own physics simulator. It wasn't available in 2001. You couldn't just download something. We wrote it from scratch. We evolved in simulation. We crossed our fingers. We printed it, and it worked. But it only worked because these were very, very simple quasi-static robots. But in general, we have what we call the simulation reality gap, which means that you can do things in simulation, but it doesn't mean that it works in reality. And all of you working in simulation know that the more complex the dynamics, the harder it is to transfer from simulation to reality. Same thing from robotics. So this approach of doing things in simulation and then crossing your fingers doesn't necessarily work. Certainly does not work in reality, in robotics. The second project, we did everything on the physical robot. There was no simulation. We just trained on the physical robot. So it sounds like we skipped the whole simulation thing. But the challenge there is, of course, that it takes too many physical trials. And there's a limit to how many trials you can do on a physical robot overnight, maybe 200, 500. It's still a far cry from what you need in order to develop a controller that can make a robot gallop in the field or really exploit the interesting dynamics that the system has to offer. So what will we do? So the third approach that we tried was a sort of a hybrid. And I'm going to start off by taking a simulator, and I'm putting this in quotes because it's going to be a bad simulator, a crude simulator. Use it to evolve robots. Try the best one in reality. Now, because the simulation is very crude, the robot is not going to work well in reality. It's going to be crappy. But you're going to collect a lot of data on how the robot performs, its actuation and sensation. Take all that data, the actuation, sensation, for example, motor commands and accelerations that the robot feels, take all that information and evolve better simulators. And this is the key idea here. So we are not evolving robots in a fixed simulation, which was what everybody else was doing. We are now going to evolve robots in a simulation, and the goal of the robots is to improve performance in the best simulator, and the goal of the simulator is to match retrospectively the experience that the robots had in reality. And that sort of combination is something we call coevolution, something that basically you're co-optimizing two things at the same time. And they have a relationship between them that is sort of like predator-prey, or maybe student-professor, kind of somewhat antagonistic, but somewhat, they both want to move forward. And this is sort of a co-evolutionary relationship, something that now is frequently called adversarial learning, and you'll hear that term a lot, is about two things that are co-optimizing at the same time, challenging each other, and gradually creating what we hope is an arms race towards a better situation. So I'll show you the third robot we built, is this one. This is a four-legged machine. It has 8 motors, 2 on each leg, and 2 sensors that can tell it how it's tilted left and right, forward and backwards. So very simple machine, 4 actuators, 2 sensors, and at least needs to learn how to walk. Now, interesting thing about this robot is that it has no clue what it looks like. It doesn't know if it's a snake, a spider, a tree. All it knows, it has 8 motors in some place and 2 sensors of tilt, and it needs to learn how to walk. So to understand what that means, you should imagine yourself for a moment sitting in a black box with no windows, and all you have in front of you are 8 knobs. And as you turn the 8 knobs, you can feel the box tilting left and right, forward and backwards, and you need to understand how to make this box move in a straight line. Let's say that's sort of the challenge that this robot has, not knowing what it is, not having a model. And also not being able to do too many experiments because it's in the physical world. This is maybe not unlike what a brain of a newborn child feels when it has actuators and sensations, and it needs to figure out what it is. So we started off by taking this robot and having it do some random motions, flailing around, babbling, if you like. And then it takes all that information and begins to create models. And you can see we use evolutionary algorithms this time to create models, not to create actual controllers or to evolve robots directly. But these are models that match retrospectively match the sensation actuation pairs that the robot actually felt. And I'll show you this in a moment. You'll see lots of models that the robot created for itself, but they're all going to be wrong. Now, you have to remember, you know that they're wrong because you happen to know what the robot really looks like. But insofar as the robot knows, these are all valid hypotheses about what it is. The next step, and that's the green box there, is going to try to figure out what action to take to cause disagreement between predictions of these models. And this is really the critical step. This is the co-evolutionary adversarial learning. So it's called sort of active learning. The idea here is that if you have three models and they all agree on something, there's no point in doing that test. But if they disagree about something, that's a good test to do, because the result from that test will refute at least one of these models. And this is sort of how we design experiments. A scientist designs an experiment whose result will cause an experiment. The best experiment to design is one that causes two theories that disagree about the prediction. And then the result will refute at least one of those theories, and this is what's going to happen here. So it looks for that disagreement or maximum variance, if you want to formalize it, between predictions of models. That's the action it's going to do. It's going to take that information, eliminate some models, improve others, keep that information, and so on and go on until it cannot make these models disagree anymore. At which point they are sort of converged. It then uses that best model to figure out how to walk. And because reality and models are not disagreeing anymore, what makes the model move forward will also make the robot move forward in reality. So here you can see one of our first attempts at running this. This is in the lab, and the robot is beginning to explore itself, to do this babbling phase where it's learning what it is. And, it sometimes works, but sometimes doesn't. And it unplugged itself. And that was the end of that experiment. And it's an interesting thing to learn that, you don't want the robot to explore too far outside of what he knows about itself, because it's dangerous. You don't want to walk off a cliff just to learn what it feels like, right? There's a cost to doing experiments. So we tamed the robot down a little bit, and here it is exploring itself. And this is about, I'd say, a day into the process, has no clue what it is. No clue what the morphology is. It knows it's made of joints and bars and motors, but doesn't know how they're connected. This is 2 days into the process, only its 8th experiment physically, a lot of computation. It's figured out it has 4 legs, but doesn't quite know where they're connected. And this is at the end of 16 trials, the end of 4 days, it pretty much figured out it has 4 legs. Now it uses that self-image it's created of itself, and it's a simple enough robot that we can peek inside and see what it's thinking about itself. And here it is learning how to move forward using its self-image, not trial and error. And here it is moving in reality for the first time. So again, this robot did not learn how to walk because it was programmed with rules. It did not do trials of walking before this. It did not have a simulation of itself. Everything is spontaneous. And we were hoping to get an evil spidery walk, but we got this lame way of moving forward. But when you look at this, we wanted to test it. We did something very cruel. We chopped off a leg, and we watched what happened. And in about a day, the robot's self-image also loses a leg. And it's not because there was a sensor that said leg came off, switch to plan B. It's because the leg came off, the dynamics changed, the self-image changed, the behavior changed. It's all spontaneous. You can see here the robot, without a leg is learning how to move again. I know it's very sad. But we did put the leg back together again. And the robot is happily retired in my office. But you can see here that all this adaptation is happening. And I started this talk talking about how adaptation is really difficult with robots, and you can see here sort of trying to get at that. So, when we published this, somebody told me that he's seen a lot of machines fail and break, but he's never seen a machine that looks like it's trying to keep on going, like this one is. It's almost, there's something sentient almost about this. Your car doesn't, when it breaks down, it doesn't really keep trying on to move forward, but this robot seems to. All right, so just to give you a little bit of statistics, if you put the robot at the origin there and you give it a random controller, it goes to the red dots on average, gives you a distribution. we're rewarding it for going vertically down. The black dots are where its self-image predicts it's going to get to, and the blue dots is where it actually gets to. So what you can see here is that, like anything else in academia, this robot has an inflated self-image. It believes it can do twice as much as it really can. Nevertheless, that self-image allows it to make the right kind of decision. And it's an interesting kind of concept here that the self-model doesn't have to be accurate to be useful. It has to sort of have the right kind, allow you to make the right kind of decisions. And some of you here are working on surrogate models for different things. I think that's an interesting insight. I gave a talk about this in a social science conference recently, and people asked, is it better to have an inflated self-image or a deflated self-image? People spend careers trying to look at these questions. This is another window into some of these deep questions. So we're doing a lot now in terms of research on the theory of mind, which is robots modeling other robots, not modeling themselves, robots modeling what other robots can and can't do, what other robots are thinking based on their behavior, whether they're planning. And of course, the idea is ultimately for robots to take that theory of mind ability and apply it to itself, which I believe will lead to self-awareness and the sort of holy grail of robotics. But that's sort of, I think, also the evolution of self-awareness, perhaps in nature. But it's a long path. So we had this robot, and it's self-simulated. And then the question is, what's next? So suddenly a new student comes into the group and says, hey, you can take that entire self-modeling process and use it to model any black box. Why only robotics? You can apply it to any dynamical system as long as you can perturb that system. And this is really important. So the robot can decide what to do in order to create this agreement between its hypotheses. Any black box where you can tweak the inputs and observe the outputs is a system that you can interrogate. And imagine there's some dynamics in the black box. You can use this algorithm to figure out what's going on in there. So this is called active learning. And I'll take the same slide I had before, but instead of a robot, I'm going to put some experimental system. Instead of actuators and sensors, I'm going to put initial conditions and things you measure about that experiment. So it's the same kind of black box with inputs and outputs. Instead of models made out of bars and motors, we can put models made out of pieces of differential equations, just different kinds of components. And instead of figuring out how to move the motors to create disagreement between the models, we figure out how to change the initial conditions to create disagreement between the models. And that entire cycle is essentially otherwise the same thing. So the big question here is only one. In the previous example, the robot could carry out its own experiments. The question here is who's going to carry out the experiments on the real experimental system. It's not easy to automate every experimental system. So it could be a human doing experiments in service of hypotheses generated by a computer. And that's one way. It's almost a turning of the tables, because suddenly the computer is writing the papers and coming up with hypotheses, and the human is doing experiments. It could be another robot, or, and this turns out to be the most practical way, that you have a huge database with lots of random experiments, and the computer, when it asks for an experiment, you go to a database and pull out what is the closest experiment you have from your huge data set. And that turns out to be a good way to decouple the experimental phase from the computational phase. But these are all sort of equivalent. So we applied it to lots of different things, and I'll start with one example. I was at Cornell University at the time, and this is a bridge I used to walk across every morning as I walked onto campus. And you can see Cornell is very easy to defend. It's like that from all sides in case Harvard comes along or something, and very easy to defend. So when you cross this bridge, you always wonder, what would happen if something would be a little weaker than it needs to be. It's a very shaky bridge. And so he said, okay, let's try to use the same approach to analyze the bridge. And I like this example because I want to show that it's not just for robotics. It's really for anything where you can measure and do something. So here's a weak point there circled in red. One of the bars a little bit weaker than it needs to be. We vibrate the bridge, we measure vibrations, we create models, we see where to put the vibrators again to create disagreement between the predictions of the models. So again, it's adversarial learning, optimizing the placement to create disagreement, optimizing the model to explain away the data. These two things fight in a predator-prey kind of relationship. And we could show that we would find the weakest link a lot faster and more accurately than conventional structural identification techniques used in civil engineering. And this is just one example. Here's another one. I have an electric circuit in a black box. I kind of drew it in gray so you can see there's something in there. You can't see it, but you can actuate it electrically in different ways. You co-evolve methods to actuate, to create disagreement between hypotheses about what's inside, and fairly quickly you can identify what's in there. Again, the language here, instead of building blocks of mechanical elements, it's building blocks of electric circuits, and you can do this. So you can identify nonlinear circuits. And this was actually used by a student who spent their PhD creating models, electrical analog circuit models of cells, of biological cells. So again, you can take this, it's almost like a translation mechanism that can look at a system and create a model that somebody can look at and actually understand. And this is really
unique.
It is, at least with all the tests that we can know, so we don't know if it's unique, but it does describe what this thing is doing. Probably not unique. Difficult to know for a nonlinear system.
Yeah, I mean,
So
the structured learning is not that easy.
yeah. So, but I don't want to talk about that. I want to talk about applying it to a particular problem, which is symbolic regression. And I'm just wondering if anybody here knows what symbolic regression is. All right, so one person, I should ask it the other way that I asked the students, who doesn't know what it is? Okay, most people don't know if they don't know. That's a good thing, right? So symbolic regression is a very interesting thing. It's this idea, you all know what linear regression is, where you have a data and you want to fit a model to it. Nonlinear regression, where you have a nonlinear model and you propose the model and you use data to fit the coefficients. Symbolic regression is when you don't even have the model and you just have the basic building blocks. So for example, here's some data, and I ask you, what is the shape of the function that fits this data? It's not a rhetoric question. Anybody want to guess?
Some kind of an exponential sinusoid.
That's perfect. That was very fast. I had a whole speech ready, but this is exponential times a sine. So if you're trying to do this in your head, you are doing symbolic regression because you actually didn't care about coefficients, but you said, okay, I know about trigonometric functions, I know about exponentials, I know about addition, subtraction. I'm trying to put this thing together to qualitatively fit the data, right? Well, actually, it's for you. What is this function? Just in case I have this. I'm kidding. This is harder. But if you're trying to do this in your head, what we can do is sort of evolve equations to fit this data. So I take this data, I take equation and I represent them as parse trees. This equation, for example, is x minus 3 times sine of x minus 7. I take my data, I generate random trees, I measure the error, I take the better trees, cross them over with other good trees, replace lower performing trees, and I gradually reduce the error, and bam, here's the answer. Okay? So you look at this and, it sounds like it's a good idea, it should work. It's proposed by John Koza in 1992. Wasn't enough computing power then. So it's a great idea. There's only one problem. It doesn't work. Why doesn't it not work? For the two problems, the curses of machine learning. One, it takes too much computing power because you need to test every model against all the data. It doesn't scale well. And the second reason is that it tends to overfit the data. You create all kinds of models, all kinds of nuances, and they argue about things that are irrelevant, and they go into deep crevices, and they overfit the data. So for those two reasons, like many other, it's a place where a lot of machine learning approaches die, is on this complexity and accuracy thing. So what we did here is basically the same idea, but we're going to use that coevolution, this adversarial learning principle. And this is what I'm going to come back to here. We're going to evolve models and have them fit the data. But here's the trick. We're not going to fit them to the entire data set. We're going to fit them to a small subset of the data, maybe 8 points out of a million. But which 8 points? The points that cause the most disagreement between the 1,000 models that we currently have. So when all the models can fit a particular area well, there's no point in testing there. The test points will move on somewhere else, okay? It's sort of like, again, a professor designing exam questions, and exam questions that everybody can get easily do not help you distinguish between good and bad students, and exam questions that are too hard do not help you. But exam questions where half the students get right and half the students get wrong is the most informative about who's learning, and this is exactly what's happening here. The points jump around to where there is disagreement between these models, and as the models learn things or forget things, the points will move around to adapt it. So here's one of our first runs. This is a prototype software. Here's this data set that I actually just showed you that you solved in your head. Here's the computer. You can see the points moving around, and bam, it gets the result pretty quickly. And it's very fast now because it only needs to measure on a few points. And in fact, if you actually look at this equation here, you can see this is sort of conventional genetic programming, try to create a model using the entire data set. These are curves when it tries to use a random subsample, a subsample that's fixed, or some subsample that's randomly moving around. So different ways of subsampling. And this is the coevolutionary process, and you can see it finds the accurate the solution more quickly and more accurately than looking at the entire data set. And this is really, really puzzling. Most people feel that more data is better. But this shows you that having the right data is more important than having lots of data. And this coevolutionary process, this adversarial learning, helps you find the right data a lot faster. This is an entire data set. This is a coevolved data set. Now here's another angle. This is for the accuracy, the size of the solution for a given accuracy. And you can see entire data set tend to create larger solutions for the same accuracy than the coevolved data set. In other words, they overfit.
So are you penalized for the overfit?
No penalty whatsoever. And I'm not sure why this is happening, but it happens systematically.
So you don't have a term for that?
No term, no regularization term. It's entirely, I think, because the functions that overfit, there's many more ways to overfit than there is to find the right solution. So disagreement is easier to find between overfitting functions, but this is entirely empirical. We don't know what happens. Okay, so what do we do with this? So first thing we try to do is predict the stock market. And I'm still here, right? So that didn't work, all right? And it did work for other people. But I'll tell you the trick later. Yeah. So it's not you just can't plug the data and hit enter and hope that it finds it. So we thought, okay, we're gonna find a formula for the prime numbers. That sounds like a good challenge. We put in the 5 prime numbers. We hit enter, nothing. We found an well-known approximation, but nothing well-known. So seeing that we're not going to get rich or famous, we decided to publish this and see what happened and write some grants. And published it, and I got an email from CERN, from Particle Accelerator in CERN in Geneva, and they said, we have the perfect problem for you. We have some gap of energy between binding energy. I don't even understand what it is. They have a ton of data. They're looking for the relationship. So we ran it. We looked at it. We got this beautiful equation that explains it very accurately. We then I emailed the guy and I said, here's the formula. What happens next? And he said, we already know about this formula. And our formula, it's called the Weizsäcker's formula, it's better than yours, right? It has 4 digits accuracy. And so they were very disappointed, but we were actually amazed. We were amazed that it can find a named formula, right? So that means that given enough data, we can find something else. Even the dean was amazed because they're going to sell a named formula, a new source of revenue. So lots of opportunities here, but the question is what's going to happen next? But we wanted to kick it up a notch and try to create dynamical system models. So not just curve fitting, but dynamical system models. So the long story short is to create dynamical system models. You take the derivative and then you do curve fitting. Because that's basically, and then you have differential equations rather than the original thing, but it's basically the same idea. Of course, there's devil in the details and how you do the derivatives of noisy data and so on. But we have time traces, we create the derivatives, and we fit those curves to create ordinary equations, differential equations. And we tested this on something here. This is 7 differential equations, coupled nonlinear differential equations that describe the glycolysis cycle in the cell. Again, I don't completely understand what that is, but it looks difficult. We took these 7 equations, we generated data out of it, with sprinkled 10% noise on it, fed it back into the system, and within about a day, it spits out these 7 differential equations almost verbatim to what the input was, the hidden input was, and all we gave it is plus, minus, divide, multiply. That's the only building blocks, and everything except that wrong but small red term there is correct. So, and again, it's not fitting the model to the data, it's coming up with a model from scratch with zero prior knowledge. So armed with this thing, I went around the country giving colloquiums like this and saying, okay, I have this hammer, I'm looking for nails. If you have data of an interesting problem that you're trying to create an analytical model of, I can't guarantee that I'll find something, but this is a tool that might be able to allow you to see something that you could not see by yourself. And nobody wanted to give me data. And if you're in that space, you know that getting data from people is really hard and challenging. But so we started working on this by ourselves on all kinds of problems. I'm going to give you 2 examples quickly before I tell you what happened later. But this is, part of our work in robotics and 3D printing, which continues in parallel. We built this flapping, hovering robot, it's 3 centimeters wingspan. It claps its wings vertically and hovers in the air like a mosquito with carrying its own battery. But one of the challenging thing about these flapping wing robots is understanding the aeroelastic behavior of the wings. Very complex, turbulent, bending, it's all coupled, no way to simulate it. So we said, okay, let's take the data from a slow-mo camera and sensors and try to see if we can create a model using our own technique. So we took all this data and we got an interesting model. Now, I'm not going to show you the model itself because that's sort of not necessarily interesting, but I want to compare it to other models on these 2 axes that are the ultimate axes for anything that has to do with machine learning: accuracy and complexity. And I would say that's also true for all of science. You can create models that are
That's true with humans, though.
the truth is the ultimate truth. That you can have models that are simple but not very accurate. That's useful for many things. You can have models that are accurate but complex, and they're also useful for anything. There's for some things, and there's lots of place in between. Here's where you get the Nobel Prize, right? In this corner, and this is where most of us end up, right? In that corner. But this is all of science, that right there. So where do the models created by the system, how do they compare to what people have been doing? So for the flapping wing problem, here are a couple of dots that represent state-of-the-art results, models. Each dot here is somebody's career. I create a model with data or or tested on data, different approaches, and here are the models created by this approach. And what's important to understand, if you look at these models, they are simpler and more accurate than models created by humans. And to me, I don't know if they're correct or not, but Occam's razor suggests they're definitely worth looking at. If they are simple and more accurate, in fact, they're more accurate than polynomial fits and all kinds of things of various degrees. There's definitely something that the machine is able to find than other people. Some of these are colleagues of mine down the hall, and they don't like this graph. So where is this going? Here's another example. This is another student walked into the lab and they wanted to model road tire interaction. I didn't know there's a field of research like that. Apparently there is. I thought, okay, this is about safety and about vehicle performance. And the guy said, no, it's about video games, making better video games. All right, so there's a whole industry devoted to modeling road tire interaction for video games. They have huge amounts of data. And they create these models, and again, the models created by the software are simpler and more accurate by orders of magnitude than anything used by industry. So again, you see this idea of adversarial learning sort of allows the system to learn faster and faster. So I keep going around the country, around the world, giving these talks about this hammer that I have, and nobody wants to give me data. But then one guy comes to me, Gurul Sewell, and he says, he was the University of Texas Southwestern at the time, now he's in San Diego, and he says, I got the perfect data for you. I have some single cell measurements that he measures cells, various chemicals going up and down in these cells over time, and he measures this at individual cell level. So not a vat of a billion cells and what's happening on average, but imagine that you can look at chemical reactions at an individual molecule level. So he has this for bacteria. He says he has 60 cells. He's measuring 2 chemicals, 2 markers in these cells, and he said, please find a model that explains these entire cells. Excuse me. So it looks like this here, the traces. He said, find a model that fits all the cells, possibly with different parameters, different coefficients for different cells, but still the same model for everybody. So he gives me this data. It's perfect. Perfect one with this. So we put it in, we hit enter, and after about a week, we get this answer. So here's the equation, here's the model, and I don't know if this is true or not. I send this to Gurul by email, and he emails me back immediately, and he says, this is total crap. Doesn't match anything, it's not even biological, nothing. Nothing here is interesting. So we were actually insulted a little bit. And we went back and we said, okay, we're doing something wrong. It cannot be that we can't solve it. So
you're not using maybe the domain knowledge to the problem.
So true. So we're thinking, okay, what do we need to put in there? So we realized after a while we're doing 2 things wrong. One is, and it's true the domain knowledge, but in what form? So we realized that first of all we're using one of the building blocks we gave it was sine and cosine, and there's no sine and cosine in biology. That's totally a physics thing. But we were missing something else that is very important to biology, and what was that building block? So we thought about it, and we decided to put in time delays. So time delays don't happen in physics, they happen in biology a lot because of all kinds of things. We put it in there, we hit enter, and bam, we get these 2 equations that explain the entire data set, fit it perfectly. I email Gurul immediately and say, here, I found the solution, and he emails me back and says, we have a problem. This is the state of the art, and your equations are simpler and more accurate. What do we do? The only problem, so it sounds like a no-brainer, but there's only one problem. We have no clue what these equations mean.
So where's your time delay in the...
These are, all the variables here have time delay. I didn't put the other, but these are time delay equations, but we don't know what they mean. It's like copying somebody's homework, and you get the result right, but you can't explain how you got it and how it works, and what these coefficients are, and so on. So it fits new cell lines that were not available at the time. It's clearly modeling something very important. And by the way, we now know what it means, but at the time we were really, really puzzled by this. We couldn't publish it anywhere. The reviewer said, if you don't know what it means, don't bother us with these equations. So that brings me to the last speech, which is searching for meaning. And I don't mean this kind of searching for meaning. I mean this very literal thing that you have a solution in your hand created by an AI system, and you have no clue into insights. You have no insight into what it means. And I want to differentiate that from all the machine learning that's happening in industry right now, which is all about prediction and not about insight. If this is real insight, this is real, example, people analyze supermarket data. They found that people that buy diapers on Thursday evening also buy beer. No. If you are a supermarket manager, you don't care why. You just move the beer next to the diapers and you sell more. But if you are a scientist, it's all about the why. What is governing this dynamics? What is the causality behind it? What is really happening there? And the long story short here is another student that came along and says, okay, it's all about finding invariance. We're going to look for the invariance in the data, not curve fitting, but we're going to find what is not changing about the data. And this is really, really tricky. So for example, I'll give you a pendulum here. This angle and angular velocity over time. And I ask you, what is not changing about angle and angular velocity of a pendulum? Is the ratio constant over time? No. Is there sum constant over time? No. What is constant about angle and angular velocity of a pendulum? Anybody guess? Not a rhetorical question. Okay, the total energy of the pendulum is constant. And it is a function of angular and angular velocity. So we call this the Hamiltonian of a double pendulum, and it is constant over time. And if you know the Hamiltonian of a double pendulum, of a pendulum, you know everything about its dynamics, what's driving it, the chaos, everything that you want to know is there. So we took some data from a double pendulum, and we said, okay, it's easy. Because we're using evolutionary algorithms, all that we need to change now, instead of equations that fit the data, we need equations that minimize the variance across the entire data set. It's the closest possible to an invariant. We change the fitness function, very easy step. We hit enter, and we watch what happens. The machine evolves equations, and after about a week, we get the result. 42, a constant. The machine developed a constant. And it's true, this function is constant across the entire data set. It's sort of baffling, but it's true. In fact, we got lots of constants that are constant across the entire data set. So we're not getting anywhere. So we went back and said, okay, we want a function that is constant across the entire data set, but uses the variables. We put in there and we got this. This is constant and it uses the variables. Okay, so another student comes along and says, I have a special library of symbolic analysis that can remove these things, and the machine cannot cheat. It has to find something. We put it in there, we penalize it for not using the variables, we do all kinds of things, and we get this answer. A little more sophisticated, you can't take the x squared out, but it's basically a constant and it's useless. And the more constant you want it to be, the larger this number becomes. So, turns out that finding invariance is very easy. It's too easy. Finding good invariance is hard. And this is sort of, we've been struggling with this. So eventually I did what most professors do, which is to give this as homework. I gave it as a homework, and I said, okay, if you, it actually was a bonus in my class. I said, if you can find a way to reward the system for finding true invariance, you get some bonus. And one student comes along, Michael Schmidt, and says, I know how to do this. You compute the derivative, the ratio between the derivatives, dx, dy, dy, dx. You take a candidate function, you compute symbolically the f dx and the f dy. The ratio between them has to match, and the system cannot cheat. It has to find a real invariant. And he hands in the 3 homework assignments. This is really the homework assignment. Here are the manifolds, here's the invariant. He finds them perfectly. So we take it, we apply it to another system. This is an oscillator, sort of the physics 101. Machine tracks this thing with a webcam, and here's what it tracks, and here's the invariant it finds. Hamiltonian also finds the Lagrangian of the system, which is the same definition. We kick it up a notch. Here's a pendulum, bubble gum on a shoestring. Bam, Hamiltonian, Lagrangian in a few hours. This is a double oscillator, 3 springs, 2 oscillators, crazy curves. What's invariant about this green and red curve? This is the invariant, and this is the Hamiltonian of a double oscillator. Again, not knowing anything about physics or geometry, but entirely by just having plus minus divide and multiply. We kick it up a notch again. We take Steve Strogatz's double pendulum, and here it is swinging it around. We track it with an LED. This is what it looks like. We put it in a big database, and we find out what's happening. And by the way, I frequently give talks to business people, and I actually start with this slide. And I say, does your business look like this? And are you looking to understand what it's doing? Then I can help you. So we take all this data, and we plug it in the system, and we ask, what is the invariant behind this crazy data? What is not changing? And this is what the actual raw data corresponding to what I just showed you looks like. And within about a day, the system comes back and says, this is invariant. And this is actually the Hamiltonian of a double pendulum, which it would be hard for me to write this from scratch, even if I practice this. It also finds F equal ma, all kinds of invariants about physics. It also finds conservation of momentum, which is true for the high energy portions of the swing. It finds all kinds of truths about this data that we can use. And by the way, we put back the data from Gurul, and we asked, what is invariant about all these cells? It found an invariant that later turned out to be sort of the level that which the cell wants to exchange genetic material with other cells. Perfectly correlated with this term, this equation that I showed you, that's what they were describing. And it describes everything about the cell cycle that we were looking at. So finding the invariants gives you a hint at meaning. So I showed you two examples to conclude, one in physics, one in biology, about inferring models from data. And there's lots of interesting things, like the ability to find building blocks in the data, in the models, because we're generating millions of models, and we can find recurring themes and motifs and use those. If it doesn't know about sine and cosine, it can discover terms that represent sine and cosine and reuse them. Lots of interesting things to do there. But at this point, we said, okay, we got to publish this. And we published it. We got a lot of press. And I started getting a lot of emails. And all the emails basically said the same thing. They said, I have data. I need to graduate. Please find something in my data. We became the bottleneck of graduation. And a lot of people were depending on us to graduate. And eventually we said, okay, we cannot get the data. We're going to release the software. It's called Eureka. It still is. You can Google it. It's misspelled, so you can find it easily. And basically, you take this data and you put in columns of data and you say, I want a relationship with Z and this and that. And you formulate all kinds of, it's like a Google search, but for data. And you can try it out for yourself. And it gives you the answer. It doesn't give you just one model. It gives you a model on this Pareto front of accuracy versus complexity. It gives you simple models that are simple but not accurate. They're not accurate, but they're simple. Models that are very accurate but are complex, and everything in between. And you can look at this and you can pick and choose a model that makes sense to you, and you can feel like you contributed to the research and you are part of the discovery. And this is actually turns out to be very important for people. They don't want the machine to give them an answer. They want to be involved. And so this turns out to be very important. And it's a good sort of interrogation tool for data. Now, of course, the student who created this immediately spun out a company, which meant I couldn't work on this in the lab anymore. Where it goes on Amazon, it does it immediately. You swipe a credit card, and it does this on many, many cores and gives you answers very quickly. What took us a day to do, the double pendulum, now works in 3 seconds on the cloud. Lots of people are using it, doing all kinds of things. Lots of companies are creating models, big and small. Many of them are not publishing. They're just using to create a small model. A radon detection company can detect radon more accurately by combining data, using new models, finite element analysis, created a lot of data, which was then used to find equations that allow this company to predict strength of materials a lot faster. Here's another paper where they took this big equation, generated data, refitted it, and found a surrogate model that captures the behavior of that model in a particular area. That's a lot simpler than the entire equation, a lot faster to evaluate. all kinds of application to this tool. As far as I know, it's still free for academic use, so you can try it out. Here's this was used in particle accelerator at Fermi Labs. Is now 5 times more accurate because it can model the nonlinearities of the detector. So lots of different applications for this. In fact, last I looked, 1.5 million models created, 91 million core hours used. So people are using it for all kinds of things. And this is very different, again, than deep learning or these other techniques which give you a black box. This gives you an analytical expression that you can use in lots of different ways. You can gain insight from, you can pretend that you came up with it on their own. So it's actually difficult for us to know who's using the software, because you can say, I came up with this equation in my dream, and it now works, right? So very difficult to know where your equations actually come from. So you can create models that are stochastic models, which is something we're doing now, where your building blocks are not deterministic, but they're sort of stochastic building blocks. You can model distribution. This is work with Ishanu Chattopadhyay that created ways to look at stochastic data and create reactions that govern that stochastic reaction. We call this inverse Gillespie models. Lots of different applications for this. One thing that is very interesting is that application that turns out to be important is you can look at data coming from different places, create a model for each data set, and compare the models rather than compare the data. And you can say these two data sets, even though they look very different, they're actually coming from the same type of behavior. And this is very interesting to draw analogies between different disciplines and so forth. So we crawled the web and collected lots of data set that people left on their website, and we could separate them out and find all kinds of interesting relationships between them. And you can look at this and say, here's my data set, and here's somebody very close to it, and either they stole your data, or they're working on a problem that's very similar. Maybe you want to contact them, right? It's like a Facebook for data scientists. So you can kind of, you can look at this and see what's happening. So lots of interesting things. In fact, you can do interesting things here, like this is lots of data that you can collect from patients. This is for neuroscience data. And if you plot, you embed these patients in 3D, based on similarity of the model, turns out that they all lie on a curve, which means all these different particular set of diseases we looked at, they all have a single order parameter. Lots of new insights by comparing models and doing this kind of analysis. We're working now on trying to find causality in earthquake and seismic data, again, using these kinds of relationships, finding where what looks the same, which kind of data is coming from the same place. Lots of interesting things, including potentially predicting earthquakes. So lots of different applications. All right, so I'll summarize, we know evolution cannot write Shakespeare, but it's interesting that evolution can find equations, can find Hamiltonians, can find scientific insight in data. It's a controversial topic. The New York Times wrote about this work. Theoretical physicists are not yet obsolete, but scientists have taken steps towards replacing themselves. And I was very careful to show you that's not the case. We still need the scientists to collect the data, to decide what building blocks to give. And I gave you examples of when we used the wrong building block, we couldn't find anything. We found garbage. So understanding what is the alphabet to give the system is really important. I think that future science will all be about searching for these frameworks and then having the machine see if that framework is good for explaining the data, rather than trying to do all that from first principle. And finally, humans are necessary to attribute meaning to the data and this to the result, and this is sort of the biggest challenge I see looking forward. Thank you.
We don't have time for questions, but we'll make some time for questions. Students first.
Grown-ups too.
Yeah, faculty as well. Yeah.
So based on these efforts and where Eureka has gone, particularly being able to do now the inverse scholastic problems, things like that, is GP a solved problem?
No, so absolutely not. So this thing, if you can sleep through AI talk and then ask the question of scalability. How does this scale to deeper problems, to more data, and so on? This approach, I would say, scales well to when you have a lot of simple equations interacting, like in chemistry. But when you have a very complex phenomenon that's coupled, it scales exponentially with the complexity of the equation. So this is not a tool that's good for everything. It's good for certain types of problems, like any other AI technique. But I would say that GP, when you use adversarial learning, performs 1,000,000 times better than if you try to do it with a fixed thing. And that's the one lesson there, that whatever you do, and that's, I would say, true for most of AI, happened in the last, I say, 2 or 3 years, that we find that two AI systems working against each other is much more powerful than an AI learning passively from a static data set. And unfortunately, most people applying AI still work with the old paradigm, one AI system, one data set. But two AI systems are substantially better than one because they challenge each other and you get that arms race, and that's the lesson. That's the meta lesson here from this journey.
Do you have to worry about bloat or anything like that because they're adversarial?
So you don't have to worry about bloat, or at least you won't worry about it less. You don't have to penalize. You don't have to put regularization terms, and also we see that in adversarial learning and GANs, that the adversarial nature takes care of a lot of the regularization automatically. So there's something about this coevolution, arms race, predator-prey, that keeps the solutions lean.
So this kind of idea has been there at least since late 70s, right? So what is new here? You still need to define your...
Yeah, I don't know what's new.
Yeah, that's what I
about
want
the
to find out.
70s. Yeah, I know. I don't know.
So it's basically the computation.
I would say that sometimes people say that it existed in the 70s, but then I ask them, why wasn't it done?
The computation wasn't there.
No, but there was a lot of computation in the 90s and nobody did this. So I don't think it's so simple that it already existed. But maybe it was. I don't know.
Was the adversarial component?
Yeah.
I mean, that's a huge step, I think, you incorporated that adversarial aspect. I mean, I don't see a lot of adversarial analysis in GPs. I mean, I see it in other
Right.
aspects of ML. But
So the adversarial thing, so there was learning by committee, there was all kinds of
The ensemble.
ensemble learning, but not so much the adversarial component. But maybe the idea was there, but it wasn't.
How about
computing power.
fake news?
Yes. So fake news, actually very relevant, can be increasingly created by systems that learn to create news and other systems that learn to spot the difference between fake and real. And these two systems challenge each other. And I've seen clickbaits created by AI that are irresistible. So you're absolutely right. And this is part of actually a growing challenge, is that the AI is learning to generate fake things better even than humans. But it's also learning to spot them. So maybe it's an arms race. It's going to be an arms race. It's a good insight there.
So how many elemental functions do you have in your system?
So this is why you come in as a scientist. So you can say only plus minus divide multiply. You can put sine cos. You can specify that. But again, the search grows exponentially the more letters you have in your alphabet. So if you originally in the software we had select all, but then people say put in everything, and then it just took forever. So now you have to at least click on each one that you want to do. But yeah, if you as a scientist know that this is biology, there's no sine and cosine, that helps immensely. This is where your prior knowledge can help. In fact, what we tend to do is, if you go to an expert and ask, what do you think the equations are, and they give you relevant equations, you can take those equations and from them parse out what are good building blocks to seed, and then allow the process.
Do you still have the feature selection problem, or is it irrelevant?
The feature selection, no, so you do the feature, so you give the data, as I said, but then it combines the data to create these meta components, like it replaces x with sine of x, and that's a feature, if you like. And it can keep track that sine of x keeps appearing.
How does it know when to stop? Or
It doesn't know when to stop.
so you stop it?
So we stop it. I mean, there's convergence. You see, it's not making progress over a long time. It runs multiple things in parallel, and when they all sort of begin to overlap with the results, there's some statistical notion of convergence, no guarantees. So you can have sort of indicators of convergence like that, but you never know for sure. If you wait a little bit longer, you might get a better result. So again, you asked about uniqueness of the solution earlier. There's no guarantees the solutions are unique. There's no guarantees that you found them. There's no guarantees whatsoever. This is like a data mining tool where you just explore and see if there's
The
anything.
nice thing about it is that you can use the domain knowledge as part of
it, right.
learning.
So
And it can be interactive. That's another nice thing about it.
So by selecting the building blocks, essentially parameterize your design space. So two questions. How well do you think this works to develop or to try to find new physics? And second, what happens? How does this behavior have multi-physics that things that interact with